So far in our discussion of molecular shapes and Lewis structures, we have taken examples where one Lewis structure was possible. However, there are molecules or ions or species for which more than one Lewis structure is possible. The actual structure is not one specific Lewis structure, but actually like an average of all possible Lewis structures. This phenomenon in chemistry is called resonance. So in the coming period, we will tackle resonance. We'll talk about resonance. We'll take examples of molecules or species or ions that exhibit resonance, and then we'll see how we can calculate formal charges for each atom in the Lewis structure. So let's begin with an example such as the nitrate ion. That's the nitrate ion. It's an O3 minus. The valence electrons in this case would be 5 from nitrogen, because nitrogen is located in group 5A, therefore it has 5 valence electrons. So 5 plus 3 atoms of oxygen, and each of them has 6 valence electrons because oxygen is located in group 6A. So 3 times 6. What we need to do next is we need to add, because the charge is negative, and we add the same magnitude, which is 1. So the total number of valence electrons in this case is 24 valence electrons in the nitrate ion case. If we divide 24 by 2, we get 12 electron pairs. So 24 divided by 2, that is 12 electron pairs. So 24 valence electrons, 12 electron pairs. So let's begin with drawing the central atom to start with. So that's nitrogen. And then oxygen, there are 3 of them. So that's oxygen, that's second, and that's third. Next step would be to draw a single bond between the central nitrogen atom and each of these oxygen atoms. Next, we need to satisfy the octet rule for each of these oxygen atoms, just to make sure that they obey the octet. So if you look at that Lewis structure, you will see that each of these oxygen atoms is actually surrounded by 8. The number of valence electrons used up so far in this Lewis structure is actually 24. And we had 24, so we don't have any more valence electrons to use. But if you look at the central nitrogen atom, you will notice that it has not satisfied the octet rule. So this is unsatisfactory. So what we should do next is we remove one of these lone pairs, and instead of drawing a single bond between nitrogen and oxygen, now we draw a double bond. So there's a double bond between nitrogen and that oxygen atom. If you look at nitrogen now, it has satisfied the octet. So it's surrounded by actually 8 electrons. Each of these oxygens is also surrounded by 8 electrons. So 8 times 3, that's 24, and that's reasonable. If you check the electron pair, so 4 here and 4 there, that is 8 plus 4, that's 12. So that's reasonable because we had 12 electron pairs before. What's next is to draw this Lewis structure between square brackets, and we put the negative charge outside the square bracket. Now, if you look carefully at this Lewis structure, you will see that the double bond is between the central nitrogen atom and that oxygen atom. What if we draw a double bond between the central nitrogen atom and that oxygen atom at the top? In other words, we move, if you like, that pi bond from here to there. Is that not possible? Of course it is possible. So this is what's called resonance, which is indicated by this strict arrow, just to indicate that there is resonance in this case. And then we draw the nitrogen atom as the central atom, but now there is a double bond between nitrogen and the oxygen at the top. So we draw the other oxygens. Now there is a single bond between nitrogen and that oxygen, a single bond here, and then we satisfy the octet obviously for each of these oxygen atoms. And then we draw the square brackets and the charge outside. If you look at these Lewis structures, these are possible. The only differ in the position of the double bond. In this case, the double bond is between nitrogen and this oxygen on the left side. In this case, the double bond is between the central nitrogen atom and the oxygen at the top. Why can't we draw a double bond between that central nitrogen atom and that oxygen? Is that not possible? It is actually possible. So therefore, we can draw a third Lewis structure connecting the second one with the third one by that resonance arrow. And then we draw the central nitrogen atom, that top oxygen, that oxygen and that oxygen. And now we draw the double bond between the central nitrogen atom and that oxygen, a single bond here, a single bond here. And then we satisfy the octet for each of these surrounding oxygen atoms. And then we draw the square bracket, the Lewis structure between square bracket. And if you look at these Lewis structures, they are all possible. They only differ again in the position of the double bond. In this case, the double bond is between that nitrogen and this oxygen. In this case, the double bond is between nitrogen and that oxygen. And then the third one is between nitrogen and oxygen on the right side. Now, these are three Lewis structures, three possible Lewis structures for the nitrate ion. Now the positions of the double bond is what's the only difference between them. Now it's found experimentally that all bonds in the nitrate ion are actually equivalent, not only in bond length but also in bond strength. This suggests that the actual structure is none of them, but actually an average of all of them, or what's called a resonance hybrid, because this phenomenon in chemistry is called resonance. So this is resonance, and the actual structure is a resonance hybrid. So therefore, the nitrate ion exhibits resonance where there is more than one possible Lewis structure. The actual structure, again, is an average of all of them, is a resonance hybrid of all of these possible Lewis structures. What about formal charges? Well, we can calculate formal charges if we consider the number of valence electrons in the free atom, and then we subtract from that number the number of valence electrons of that atom in the drawn Lewis structure. So how do we do that? Well, we can calculate formal charges by doing so. So this will be the valence electrons in the free atom minus the number of valence electrons in the structure, in the Lewis structure that we have drawn. To do that, what we need to do is we need to add up the non-bonding electrons, and then we subtract, or divide the bonding electrons by 2. So basically we need to add up the non-bonding electrons and half of the bonding electrons for each atom. So what we need to write here is non-bonding plus half bonding. Let's try to practice that. If we take, for example, this oxygen atom, the number of valence electrons for oxygen is 6 in the free atom. The number of non-bonding electrons in the Lewis structure is 6. Half of the bonding is actually 1 because there are 2 bonding electrons between oxygen and nitrogen. So there are 7 valence electrons on oxygen in this Lewis structure. We subtract that number from 6. So in this case of oxygen, it will be 6 minus 7, and the formal charge here will be minus 1. So it's minus 1 for that oxygen. If you look at the other oxygen, the number of non-bonding electrons in this structure is 4. Half of bonding is 2. So 4 plus 2, that is the total number of valence electrons in the structure. So 4 plus 2, that is 6. We subtract 6 from the number of valence electrons of oxygen in the free atom, if you like, or in the free state. So 6 minus 6, so that is 0. So it is 0 here. The formal charge of oxygen in this Lewis structure of that specific oxygen is actually 0. If you look at that oxygen, it's 6 non-bonding plus 1, that's 7. 7 from 6, which is the number of valence electrons in the free atom. So 6 minus 7, that is minus 1. So it is minus 1 for that oxygen. For the central nitrogen atom, the number of valence electrons in the free atom is actually 5. Again, that's because nitrogen is located in group 5A. The number of non-bonding electrons is 0, but the number of bonding electrons is 8. We divide 8 by 2, that is 4. So 4 from 5, and that is plus 1. So the formal charge of nitrogen in this case is plus 1. If you add these formal charges up, so 0 plus 1 minus 1 minus 1, the total or the sum should be minus 1, which is the overall charge of the molecule, of the ion. So the sum will be 0 plus 1 minus 1 minus 1, and that is minus 1. And that is reasonable because the overall charge is also minus 1. If you look at this lowest structure, to calculate the formal charge, we do the same practice. The number of non-bonding electrons on nitrogen in this lowest structure is actually 0. If we divide the bonding electrons by 2, we get 4. 4 from 5, that is plus. So it is plus 1. In this case, for nitrogen, for that oxygen, 4 non-bonding electrons, 4 bonding electrons, but we divide that by 2. So 2 plus 4, that is 6. We subtract 6 from 6, which is the number of valence electrons of oxygen in the free state, and that is 0. So the formal charge of this oxygen atom is actually 0. For that oxygen atom, the number of non-bonding electrons is 6. The number of bonding electrons is 2. We divide by 2, we get 1. So 1 plus 6, that is 7. 7 from 6, that is minus 1. So the formal charge of oxygen here, it is minus 1, and the formal charge here should also be minus 1, which suggests that if oxygen makes one bond unusually, then the formal charge should be minus 1, because oxygen usually makes 2 bonds, just like in water basically. That's because oxygen is located in group 6A. That's because oxygen has 6 valence electrons, and that's because it needs 2 electrons more in order to satisfy the octet. Nitrogen here makes more bonds than usual, and that's why the formal charge is plus 1. Nitrogen usually makes 3 bonds because it's located in group 5A. Therefore, it needs 3 electrons in order to satisfy the octet. Moving on to the last structure, the formal charge here is also plus 1. The formal charge here is minus 1 here, and here 0. And if you add all of these formal charges together, you will see minus 1 plus 0 plus minus 1. The total should be minus 1. Otherwise, there is a mistake, and there isn't. Minus 1 plus 1 in the last one, minus 1 plus 0 should give minus 1, and it does. So that's actually always true, that the sum of atomic formal charges, if you like, should give us the total charge of the ion. In summary, in this case, the nitrate ion is a typical example that exhibits this phenomenon of resonance.